Welcome back to the second video for TEC 293 on Tuesday, April 6th. In this video, we're going to continue our discussion of beam bending. In the first video, we identified 4 different factors that affect how much deflection a beam is going to have when you apply a load to it, and how much force it can support before it fails. Those 4 factors that are important were the material that you make the beam out of, because that affects something called the flexural modulus. The second was the geometry of the beam, not just the cross-sectional area like we had in tensile testing or compression testing. Remember, all that really mattered for tensile and compression testing was the cross-sectional area. But for beam bending, it's not just the cross-sectional area, it's actually the geometry and the shape of the part, because that affects something called the moment of inertia. So we talked about that in the first video. And the third thing was the way that the beam is supported, for example, as a cantilever beam, or as a simply supported beam, or as a beam that's fixed on both sides. And the fourth thing that we talked about was the way the load is applied. For example, is it a point load applied in the middle, or is it an evenly, uniformly distributed load, kind of like a bookshelf? So those are the 4 things that we identified as being important to consider when we're looking at beam bending situations. And in the first video, we talked in more detail about the first 2 of those, the material property called the flexural modulus, and the geometry of the beam, which affects the moment of inertia. And we talked about how to calculate the moment of inertia. And we said that when you multiply those 2 things together, when you take E sub B times I, that is the flexural modulus times the moment of inertia, you get a term called the flexural rigidity, And that is the rigidity of the beam due to its material that it's made out of and the shape of the beam. The other factors that we're going to talk about in this video in more detail are the way the beam is supported and also how the load is applied to the beam. So those are the last 2 things that we have to talk about. When we consider all of those things together, we can come up with some equations, and I'm going to give you some equations in this video. We're going to have some equations for the deflection of the beam and some equations for the stress in the beam. So when I give you those equations, the deflection equations are going to be for the point on the beam where you have the maximum deflection. So that's the deflection that you're finding when you're applying these deflection equations, the maximum deflection of the beam. For the stress equations, it's similar. Those stress equations that we're going to talk about momentarily, those are the equations for the point in the beam where you have the maximum stress. So that's going to be the maximum stress in the beam. Not every point in the beam is going to be subjected to the exact same stress, just like not every point in the beam is going to deflect the same amount. You can probably imagine that some points on the beam are going to deflect more because the beam's naturally going to sag depending on where you apply the load. So when we apply these equations for deflection and stress, that's going to be for the point in the beam that has the most deflection for the deflection equations, and the point in the beam that has the most stress for the stress equations. So let's go ahead and get started, and we'll talk about those remaining factors relevant to beam bending. All right, let's talk about how the beam is supported, otherwise known as end conditions of the beam, and let's talk about how the load is distributed on the beam as well. We're going to make things a little bit simpler, well, okay, a lot simpler in this course, and we're not going to study every different possible combination of how the beam is supported and how the load is applied. We're going to narrow it down, and we're only going to talk about these 4 different situations. There's only 4 of them. So it could be a lot worse. We could be talking about an infinite number of ways that you apply the load and ways that you support the beam. There are only a limited number of ways you can support the beam, but there are an unlimited number of ways where you could apply the load. You could apply it unevenly, you could apply the load like a hyperbola. There are literally an infinite number of ways that you could apply the load to the beam. But we're only going to consider 2 different support conditions and 2 different loading conditions. So there are 4 total situations that we're going to talk about. So for each of these 4 different situations, we're going to have a different equation for the amount of deflection in the beam. And for each of these equations, in a few slides, we're going to have a different equation for the amount of stress in the beam. All right, so in this video, I'm going to give you 8 different equations. You don't have to memorize them. You just have to know how to use them. They're also in your lab manual, and you can use your lab manual or any notes that you want on the exam. So don't freak out. It's 8 equations, but they're pretty similar. They're going to look very similar to each other, and you just have to know how to use them. So what are the 4 different situations? Well, we could have a cantilever beam with a point load applied at the tip. That's scenario number 1. We could have a cantilever beam with an evenly, uniformly distributed load. That's situation number 2. We could have a simply supported beam. That just means it's just resting on these 2 points at the end of the span. So this is the beam, and this simply supported beam has a point load applied in the middle, and this simply supported beam has an evenly, uniformly distributed load throughout the span of the beam. So those are our 4 different situations that we're going to consider. And this is, obviously limiting the applicability because we're only talking about 4 different situations. But the reason I picked these 4 different situations is because these are 4 very common situations, and they're a very good approximation to a lot of different situations in the real world. We're going to talk about the equations for deflection first. That is the maximum amount of deflection that the beam is going to have. But before I show you those equations, I want to show you what the form of those equations is going to look like. We're not going to derive the equations in this class, not because it's terribly difficult, but because it does require a little bit of calculus. And calculus is not a prereq for this course. And so we're not going to derive these equations. That's why I'm just going to give you these equations. And you just need to know how to use them and apply them. So when I show you these equations, what you're going to have is the deflection. Remember from the first video that is symbolized by the lowercase Greek letter delta. So you're going to have delta max, that's the maximum deflection in the beam, which will happen right here in the middle for a simply supported beam, or at the tip of a cantilever beam. The maximum deflection is equal to some constant. This is a numeric value that's different for each of the 4 situations, times this value right here. And in the numerator here, you're going to have the load, which is the force, F, times the span, which is the distance between the supports for a cantilever beam, for a simply supported beam, or for a cantilever beam, it's the length of the beam. And we actually take the span and we cube it. So the span makes a big, big difference. If I have twice the span, 2 cubed is 8. So if I double the span of the beam, then I'm going to get 8 times the deflection, because I'm taking the span to the 3rd power. All right, and then always what you're going to see in the denominator of these deflections equations is the flexural rigidity, which we talked about in the last video. It's how rigid that specimen is, and the rigidity is due to both of these things. It's due to the rigidity of the material from the flexural modulus, as well as the rigidity of the shape of the part due to the moment of inertia. So you're always, for these deflection equations, you're always going to calculate the flexural rigidity, and that's going to be in the denominator of each of these 4 equations that I show you next. All right? So really, the only way that these equations differ, these 4 equations differ from each other, is this constant right here. This constant value is going to be a different constant for each of those 4 different situations. All right? So here are situation 1 and 2, the cantilever beams. So for a cantilever beam, we have delta max, that is the maximum deflection, which will always occur at the tip of the beam, and that is equal to 1/3. So notice there's nothing in the numerator in terms of a number, so you can consider it to be a 1. And we have this 3 in the denominator. So our constant is 1/3 times FL cubed, like we talked about before, divided by the flexural rigidity, EI. All right, so that's the form that you would use to calculate the deflection for a cantilever beam with a point load applied at the tip. 1/3 FL cubed divided by EI. All right, you'll see that a lot of these are going to look really similar. All right, now let's say we have a cantilever beam with an evenly or uniformly distributed load across that beam. What we have is we have WL to the fourth, and W is the distributed load. So W is like a number of pounds force per foot. So let's say that we have 5 pounds force per foot. That's W. And let's say the length or span of the beam is, let's say, 2 feet. So if you have your W equals 5 pounds force per foot, and your length of the beam is 2 feet, then you take 5 pounds force per foot times 2 feet, and you get 10 pounds force. All right, so usually I would recommend getting it into the total force, F. F is the total force, and you get that by taking the uniformly distributed load times the length. And once you get that, you'll get F in terms of pounds force. All right, so what I would recommend doing is you don't really need to remember this. I would not use this part right here. What I would recommend using is this equation right here to find the total force given the uniformly applied load and the length or span of the beam, and then applying that F to this equation right here. So if it were me, the equation I normally use is this equation after I calculate F, which I get from this equation over here. All right, makes sense? All right, so for practical purposes, you can really ignore this part of the equation right here, as long as you're comfortable using this equation to find the total force on this beam. So after that, we can just use this equation. Our constant here is 1/8, because we have 8 in the denominator. 1/8 times our same values, FL cubed divided by EI. So the difference here is between these two is that up here we had 1/3 as the constant, and down here we have 1/8 as the constant. And just recognize and remember that down here you have to calculate F. F is the total force applied to the beam, and you get that by multiplying the uniform load times the length of the beam. All right. One important thing that I need to say and emphasize right here is that these equations for deflection are only valid in the elastic region. They're only valid before you get to what we're going to call the flexural yield stress. So you have to make sure that your stress, we'll get to this in a few slides, but you have to make sure that your stress is less than the flexural yield stress in order to use these equations. This is just like what we did when we did tensile testing problems, right? In order to calculate the strain or something, we had to make sure that our stress in the part was not more than the yield stress, right? Because we knew in tensile testing, we knew that our equations were only valid in the elastic region because our elastic modulus was only valid in the elastic region. Very similar here, our flexural modulus here is very analogous to the elastic modulus in tension. This is only valid in the elastic region up until the flexural yield stress. All right, so very similar idea. You can use these equations only in the elastic region before you get to the flexural yield stress. Okay, here are the deflection equations for the remaining two situations. Situation 3 was a simply supported beam with a point load applied in the middle. So the form of the equation is very similar, but the constant here is 1/48 FL cubed divided by EI. All right, so whereas before we had 1/3 and we had 1/8 for the cantilever beams, now we have 1/48 for the simply supported beam with a point load applied in the middle. And for the final situation, situation number 4, we have a simply supported beam with a uniformly distributed load. Once again, What you want to do is calculate the total load first. So that's F. And then once again, it's equal to the uniform load, force per foot, times the span or length of the beam. That will get you your total force, say in pounds force. And then you plug that number into your equation over here. So once again, I would recommend that you never even really need to use this equation right here. I would recommend doing this in 2 steps. Do this type of problem in 2 steps when you have a uniform load. First, find F. Second, plug it into this part of the equation right here. And the constant here is 5/384, which is a weird number. It just happens to work out that way when you derive the equation that the constant for a simply supported beam with a uniformly applied load is 5/384. But the rest of the equation is the same. You've got FL cubed divided by EI, flexural rigidity. And once more, a reminder that these equations are only applicable in the elastic region when the maximum stress in the beam is less than what we call the flexural yield stress, because this value right here, the flexural modulus, is only valid in that elastic region. All right, so that's half of the equations that I'm going to give you in this presentation. Not so bad, right? They're all pretty similar, just the constants change between the different situations. And the other 4 equations I'm going to give you in a couple of slides are the equations for the stress in the beam, because you're going to want to calculate the maximum stress in the beam. But before we talk about that, I want to note that you can use those equations for deflection, like this one. This was the simply supported beam with a point load applied in the middle, like this. You can use this equation that I gave you, and you can find the flexural modulus from experimental data. Right? We did this before. We did this for tensile testing and compression testing. And now I just want to point out that you can do a very similar thing with flexural testing as well. Because if you do the test experimentally, then you can find out what the force was, what the span was. You can calculate the moment of inertia from the geometry of the beam, and you can measure the amount of deflection that it had in the test. So you can use this equation, and if you do the experiment on it, then your only unknown is the flexural modulus. So you can manipulate this algebraically, multiply both sides times the flexural modulus to get it over here, and then divide both sides by the maximum deflection when you had that force applied. And now you've got the maximum deflection in the denominator over here, and now you've got an equation for the flexural modulus of that material, given all the experimental data and the geometry of the situation as well. So this is how you can calculate the flexural modulus of a beam with experimental data. Once again, remember, this only applies to elastic deformation, so we have to make sure that our stress in the beam is less than the flexural yield stress. All right, so switching gears slightly, we're going to talk about the stress in the beam. Where is the point of maximum stress in the beam? We already kind of talked about this. The point of maximum stress in the beam is at the bottom side of the beam where it's in tension. So this is the critical area on the beam. And chances are that in Lab 8, when your beams fail, most of you, if not all of you, are going to experience beam failure at this location down here. This is by far the most common way that beams fail, due to exceeding the flexural strength. We'll talk about that term in a little bit, but by exceeding the flexural strength at the bottom of the beam where it's in tension. All right, so this is where the point of maximum stress is. So these equations that I'm going to give you in just a second here are for the maximum stress in the beam. So where does that maximum stress occur? It's right here. And that's where you'll see it fail, because that's where you have the maximum stress in the beam. All right. This can change a little bit. I'll make this note right here. If your beam is not symmetrical from the top half to the bottom half, then this can change a little bit. But for the purpose of our class in TEC 293, then we're going to assume that the beams are symmetric, and therefore it makes the calculations a lot easier. All right. So when I give you these equations for stress, the form of these equations, all four of them, are going to be very similar. And once again, what's going to change is this constant value. But the form for the stress is going to be a little bit different. So what you're going to see for all of these four equations I'm about to give you, you're going to see that the stress, and that is the maximum stress in the beam, is equal to some constant value times FLH, so that is the force applied, times the length or span of the beam, times the height, and that is literally the height of the beam. This is kind of like in the moment of inertia equation. When we had the h, that's the same h as we have here. This is the total height of the beam. And we're taking this divided by the moment of inertia, I. Notice that there is no flexural modulus in this equation. E sub b does not occur anywhere in this equation. Therefore, these equations are valid even above the flexural yield stress. So this is kind of like in tensile testing, we could say that stress is always equal to force divided by area, right? That equation didn't change if we were above the yield stress. We could always say that stress is equal to force divided by area for tensile or compressive testing. Same type of thing here. We're calculating the stress, and to calculate the stress, it doesn't matter if we're above or below the flexural yield stress. And that's because E sub b doesn't appear anywhere in here. All right, so this is valid anywhere in the test. And the only thing that's going to change in these equations is this constant right here. So this is the equation for cantilever beam with a point load applied at the tip. By the way, while I'm thinking about this, we talked about where is the maximum stress in the beam for a simply supported beam. Where do you think the point of maximum stress is for a cantilever beam? It's different. It's a different location. As it turns out, the point of maximum stress in a cantilever beam is right there. It's on the top surface of the beam because the top is in tension for a cantilever beam, and the point where you have the maximum stress is all the way back here at the root or the base of the cantilever, and it's on the top side right there. All right, so the most common place to see a cantilever beam fail is right there on the top side at the base of the cantilever. So that's our point load applied at the tip of the cantilever. If we have an evenly distributed load applied to our cantilever, then once again, calculate your total force F by taking your uniformly distributed load W times the length or span of the beam. That will get you F, and then plug F into this equation right here. And if you want to, you can ignore this equation. There's never a situation where you have to use this equation right here. You can always use the combination of this equation and this equation, which I think is more intuitive and easier. So that F that you calculate right here, plug that in right here. And your constant value right here is 1/4. So it's 1/2 for a cantilever beam with a point load. It's 1/4 for a cantilever beam with a uniformly distributed load. And of course, our units are PSI. Just like stress for any other equation that we've used in this class. For the other two cases, for the simply supported beams with a point load, same form of the equation, but our constant is 1/8. And for the last situation where we have a simply supported beam with a uniformly distributed load, calculate the force from the product of the uniformly distributed load times the span. Plug that F into this equation right here, where our constant is 1/16. So the maximum stress, which is at the center of the beam on the bottom surface, the maximum stress is equal to 1/16 FLH divided by I. and the units are PSI. So one more thing I'll point out about these equations. Intuitively, would you expect that you're going to have a larger stress in a situation where you have a point load or in a situation where you have a uniformly distributed load? Think back to the beginning of the first video, and I kind of talked about this when I was doing a little experiment down in the classroom down there. And I said that if there was a way to distribute the load more evenly or over a wider surface, then it could hold more load. It could hold a greater amount of force before it breaks. So if that's true, and I think that's kind of intuitive, then you would expect that the stress in the beam for a given force to be less for a uniformly distributed load than it is for a point load, right? You would expect that. If it's capable of holding more load with a uniformly distributed load, then you would expect the maximum stress in the beam to be lower with a uniformly distributed load than it is for a point load. And we can see that's true without even knowing what the F or the L or the H or the I are. You can already see that for a given force, either a point load or a distributed force, and a given span and a given height and a given moment of inertia, so the same beam over the same span and the same total force, you're going to get only a smaller amount of stress in the uniformly distributed load because you have a 1/16th for the constant here and you have 1/8 for a constant here. 1/8 is twice as large as 1/16th. So if all of the other things are the same between these two beams and the only difference is the application of the load, your stress is going to be twice as much right here at the point of maximum stress for the simply supported beam with a point load than it would be for a simply supported beam with a uniformly distributed load. I could make the same connection up here where we could say that you would expect that it would have less deflection if you have a uniform load compared to a point load, and we can see that because we have less stress right here. So here we have 1/4 for the constant, here we have 1/2 for the constant. 1/2 is twice as big as 1/4, and so for this situation you have twice the amount of maximum stress in the beam right here than you do right there. So now we have 4 equations for deflection of the beam, and now we have 4 equations for the stress in the beam, the maximum stress that you're going to get in the beam. And so now for a given loading condition and geometry of the beam, you can calculate what is the maximum stress in the beam. A few more terms to define that probably are not too surprising to you, but we can define a term called the flexural yield strength, and that is the maximum stress in the beam before you start to get plastic deformation. Very similar to the yield stress that we've talked about for many weeks already in this class, but now we're applying it to flexural testing, beam bending. And the analogous term to ultimate tensile strength, that was the maximum stress that you can get in the beam, right, in the specimen, right? Now we're talking about beam bending, and the analogous term is flexural strength. Flexural strength is the maximum stress that the beam can withstand before it fails. It's destroyed. The other term that is synonymous with flexural strength is modulus of rupture, sometimes abbreviated MOR, modulus of rupture. So these two values, the flexural yield strength and the flexural strength, aka modulus of rupture, those are material properties. Those are properties of the material. So you can look this up on matweb.com or whatever other resource you want to use, and you can find this. And in fact, this is going to be useful for you in Lab 8 when you're making your predictions for how much force your beam can support. All right, because if we have these equations, like I showed you before, if we have this equation for stress, given the material properties and given the geometry of the beam and the loading conditions, if I know how much stress the beam can support, this is the maximum stress it can have, then I can use that equation and I can find the maximum force, right? So now you can predict when the beam is going to start to undergo plastic deformation. And now you can predict when the beam is going to fail. Because what you can do, let me go back to the previous slide here. This is going to be our test situation in lab 8. We're going to have a simply supported beam with a point load applied in the middle. So what you can do is you can look up the modulus of rupture or flexural strength, they're synonymous, for whatever type of wood you use in lab 8. And I'll have a variety that you can use, you can pick from. And you can look up that flexural modulus. So that is the maximum stress that you can withstand, that material can withstand. So you can set that value equal to this value, and then you'll already know the value of the span. It's 18 inches. I'm telling you that right now. The length of the span is 18 inches for lab 8. The height of the beam is whatever you choose for the height of the beam that you design. And the moment of inertia, again, depends on the design of your beam. So using that, you can predict the F at which you're going to reach the stress that it fails. So once you look up the flexural once you look up the flexural strength of your material, you can solve for the F that is going to cause the material to fail. So that is the way that you can make your prediction in lab 8 for when your beam is going to fail. The last thing for today's video is a little application here. We've got a beam bending test for 3 different specimens, which gave us 3 different curves. And we want to identify which of these specimens corresponds to which of these curves. First of all, let me point out that this plot is the flexural load in pounds force on the vertical axis, and the horizontal axis is the flexural extension, aka deformation in inches. So how much did it deform in inches? This is not a stress strain curve. And the reason for that is we could calculate stress no problem, right? I gave you some equations for stress, so we can calculate the maximum stress in the beam without any difficulty, really. The problem is, what is strain for a beam bending test? There isn't really a good analogy for strain in flexure testing or beam bending. We could probably invent something. I mean, we could probably say that, all right, the analog or the analogous term for strain is going to be, I don't know, deflection divided by span. That would be maybe reasonable, but it's not common. That is not an industry common calculation or parameter. So we don't. So normally for flexure testing, we don't plot the data in a stress strain curve. We just plot it in a curve like this, with load in pounds force on the vertical axis and deflection or extension in inches on the horizontal axis. All right, so that was a brief aside. So good news, you're not going to be doing any more stress strain curves, at least for lab 8. No stress strain curves for lab 8, just these kind of curves. So the question is, we've got curve A, curve B, and curve C, and we got 3 specimens, a 1 by 1 by 12, a 1 by 1 by 24, and a 1 by 2 by 12. It doesn't really matter what the units are here. Let's just say they're inches. Doesn't really matter. And we want to pick out which one of these corresponds to each one of these curves. All right, so 1 by 1 means it has a base of 1 inch and a height of 1 inch and a length or span of 12 inches. This has a base of 1 inch, or width of 1 inch, a height of 1 inch, and a span of 24 inches. This one has a base of 1 inch, a height of 2 inches, and a span or length of 12 inches. All right. So look at these curves right here. This curve right here, curve A, has the least amount of deflection for a given amount of force, right? So for a given amount of force, let's say 200 pounds force, curve A, or specimen A, deflects the least. All right. Conversely, for a given amount of force, curve or specimen C deflects the most. So specimen C has the most deflection for a given amount of force. So let's look at curve A again. Curve A has the least amount of deflection for a given amount of force. So which one of these specimens do you think would be the most rigid? Which would be the most rigid part? Well, we have to assume they're all made out of the same material. So the only thing that would really change is the moment of inertia for these parts. And the moment of inertia for this one right here, for a 1/2, is going to be significantly higher than the moment of inertia for a 1/1. So this one right here, the 1/2, must be curve A, because this has the highest moment of inertia, which is going to mean that it's going to deflect the least for a given amount of force applied. So this is going to be curve A. Specimen A is going to be right here. What's going to be for these two right here? Well, the only difference is the span, actually. All right, and if you remember the equations for deflection, the deflection equations all had some constant times FL cubed divided by EI. And the important thing for right now is the L cubed. All right, so if you increase the span, you're going to drastically increase the deflection. All right, so that tells us which one is which, because curve C had the most amount of deflection for a given amount of load. So this one, curve C, must have the larger span. So this must be curve C with a larger span, and that leaves the one in the middle, so it must be B up here. So it must be B, then C, then A down here. B and C and A. Good. All right. All right. That is going to wrap up the material that I wanted to cover today. So this is actually all the material. This is all of the information about beam bending and flexure testing. What's left is applying the material. So we're going to have some calculations that we're going to go over in the next class period. And that's all we're going to do in the next class period. We're going to apply these calculation problems. We're going to apply these equations to solve different problems, a lot like we solved problems for tensile testing and compression testing. What I would strongly recommend you do before the next class video, before watching the next video, is to try to solve the example problems that I give you in the lab manual. There are 2 beam bending practice worksheets. One is on page 87 and 88, and the other is on page 89 and, well, that's it, just page 89. So these are great example problems. The next exam is going to have beam bending problems on it, and those problems will look pretty similar, not identical, but pretty similar to what you see on pages 87 through 89. So I will review those in the next video for the next class session. But you'll get a lot more out of it. You'll learn a lot more and be better prepared for the exam if you give it a shot first. It doesn't matter if you get them wrong. Just try to think through how to solve these problems. That's, at this point, the most important part, is thinking through how to solve them, not whether you get the right answer or not. You'll work on that later. But right now, just think through how to solve them, try to solve them, and then you can follow along with me in the next class session when I go through these example problems. All right, so that'll wrap things up for today. This is all the material on beam bending and flexure testing. I'll see you next time when we solve some problems using this information. See you next time.